Let's take a look at balanced and unbalanced forces. We'll concentrate on the first diagram, the motorcyclist. You can see that the forward force is 50 newtons and the backward force is 50 newtons acting on the motorcyclist. So in this situation, we can confidently say that the forces are balanced. Now when the forces are balanced, we can say two important things. We can say, one, it's not going to accelerate. And secondly, it's going to be moving at a constant velocity, or it could be sitting still. So when the forces are balanced, the main thing to note is it's not going to accelerate. Let's take a look at the P&O ferry down below. Now in this situation, the forces are definitely unbalanced. As we can see here, we have a forward force acting on the ferry as 5,000 newtons and a backward force of 1,000 newtons. So in this case, we have an unbalanced force. So that P&O ferry will accelerate. And it'll accelerate because the unbalanced force acting on it is going to be equal to 4,000 newtons. And the direction of the unbalanced force, or the resultant force, is going to be to the right. You can see it's almost like a tug of war. 5,000 newtons to the right, 1,000 newtons back away. The winning force is to the right by 4,000 newtons. And that's the unbalanced force. If we look at the space shuttle, we can see we've got forces acting to the left and to the right and up and down. But if we look at the up and down forces acting on the space shuttle, then these forces are balanced. So therefore the space shuttle is not going to be accelerating in the up and down direction. So in the up and down direction, the forces are balanced. But in the horizontal direction, the forces are unbalanced. You have 1,000 newtons playing 900 newtons, and therefore you're going to have an unbalanced force acting to the right this time of 100 newtons. So in this particular case, the space shuttle will have a horizontal unbalanced force equal to 100 newtons to the right, because that's the winning force to the right here. But in the vertical direction, the forces are balanced. So this means that the space shuttle will accelerate towards the right. Regarding the up and down movement, two things could be happening. It could be at rest, forces balanced, or it could be moving either up or down with a constant speed, or a constant speed, because the forces are balanced and there's no acceleration. Balanced and unbalanced forces. Now we'll take a look at how we can calculate the acceleration of objects using Newton's famous second law equation. Let's use Newton's second law of motion to work out the acceleration of this sports car. We're going to use the equation Fun equals ma, where Fun equals the unbalanced force, and m is the mass of the object, and a is going to be its acceleration caused by this unbalanced force. So right away we can put down a list of all our data. So Fun is the unbalanced force, m is going to be the mass of the object, and a is going to be the acceleration, which we're going to try and find. Now the unbalanced force acting on the object is going to be 400 newtons to the right. And we can see that because we have got 500 newtons to the right and 100 newtons acting back the way. So the resultant force is going to be 400 newtons to the right. And I use a little arrow there to show it's towards the right, because that's where the acceleration will be. The mass of the car is 800 kilograms. And all we have to do is find the acceleration. Now that means rearranging the unbalanced force equals ma equation. And if you do that, we get acceleration is going to be equal to the unbalanced force, Fun, divided by the mass of the car. So we'll put in our numbers and we get an answer of 400 newtons divided by the mass, which is 800 kilograms. And we're going to get an acceleration of 0.5 meters per second every second. That's how we pronounce those units. Now what does that mean? It means that when there's a force of 400 newtons acting on that car, the unbalanced force of 400 newtons is going to produce an acceleration of that car of 0.5 meters per second every second to the right, which means the speed of the car is going to increase by 0.5 meters per second every second of its journey. Okay, here's a second example for Newton's second law using the equation unbalanced force Fun equals ma. And we're dealing with a small yacht of mass 100 kilograms, and we have the following forces acting on it. First thing you do is identify whether we're going to have an acceleration or not. Well, in this case we're going to, because we're going to have an unbalanced force to the left. 75 newtons to the left and 50 newtons to the right is going to give us an unbalanced force of 25 newtons to the left. So let's put in our data. The unbalanced force, we can see from the diagram, is going to be 25 newtons, and it's going to be going towards the left this time. The mass of the small yacht is going to be 100 kilograms, and our job is to find the acceleration of it. So once again we rearrange the Fun equals ma equation to have acceleration is going to be equal to unbalanced force divided by the mass, and that's going to be equal to 25 newtons divided by 100 kilograms, and we work that out, we're going to get an answer of 0.25 meters per second every second. And it's going to be accelerating towards the left this time, because that's where the resultant force is pointing to. Remember, the acceleration of 0.25 meters per second every second means that the small yacht is going to increase its speed by 0.25 meters per second every second when moving towards the left.